Welcome to our second episode of HumanX Medical Case Studies. My name is Caroline and I will guide you through this case. As in our last video, we will use this case to explore how to create a customized model for patient-specific training. This case was provided 6 days before the planned surgical intervention by a local hospital. The 39-year-old patient was diagnosed with an instability in the pelvis caused by a slip and fall, which refractured a previous pelvic ring fracture. In order to keep the patient's ability to give birth in the future, the physicians decided not to readjust the pelvis in the area of the symphysis. Instead, they chose to stabilize the pelvic ring in its current position by implanting an iliac crest bone graft. A key requirement for the model was therefore the option to use it for planning and training the harvesting and implantation of the bone graft. The hospital provided the CT scan in DICOM format with a high resolution. The only downside was the artifacts caused by the already existing implant. Despite this limitation, this is a relatively simple case that can be easily implemented in a 3D printed model. A look at our HumanX score for 3D modeling and printing shows that the model is very well printable. As the bony structures are easily identifiable on CT, the segmentation does not present any major challenges. Due to the size of the model, a longer printing time can be expected. This must be taken into account with regard to the scheduled operation date. Using the software 3D Slicer, we segment all relevant structures from the CT scan. You can find a link to download the software in the description below. After cropping the volume to the desired region of interest, we use the segmentation module to mark the bony structures and the pre-existing screw. Since we will be using the grow from seeds algorithm, we only need to mark the structures in a few layers. The software will then use these seeds as a base reference for automatic segmentation of the remaining structures. After the first execution of the grow from seeds algorithm, we check the result layer by layer. Areas which have not been segmented correctly are manually redrawn. The algorithm then uses the adjusted markings to update the result. An initial rendering of the segmented structures gives us a first impression of the 3D model. It also shows some areas that need to be reworked manually. By also using the available coronal and sagittal views of the DICOM dataset, we try to capture as many details as possible. This iterative method helps us to ensure that all necessary areas are highlighted. This is important especially where low contrast limits the correct segmentation by an automatic algorithm. The final rendering of the segmentation looks quite impressive. But there are still some holes and gaps that could lead to longer printing times or even failed prints when using the data for 3D manufacturing. So instead of working over each layer and trying to remove the faulty areas, we will use another software to repair the model and prepare it for a successful print. In this case, we are using MeshMixer for 3D modeling. You can find a link to the official website in the description below. But you can also use Blender, Tinkercad, or any other 3D design program. After importing, the 3D model is checked for defects and inconsistencies. Remaining gaps and holes are filled to get a closed surface. Internal structures representing the spongiosa are also eliminated, as they will be mimicked by the infill structures of the final printed model. When working on the digital model, it is important to be very careful not to change the size of the model or remove relevant structures. Remember that the final product must be a detailed replica of the patient's anatomy. Otherwise, misinterpretations may occur, increasing the risk to the patient and prolonging the duration of the surgical procedure. It is therefore always helpful to re-import the final digital model into the software used for the initial segmentation and compare the result with the original DICOM images. Depending on the model, the post-modeling process can take some time. In this case, it took us about 1.5 hours from start to finish. If the model does not have critical defects, it still can be sent to the 3D printer without post-modeling. But this might result in a significantly longer print time and higher risks of failure during printing. That's why we are recommending to at least check the model and run through some basic modeling steps to avoid some potential risks. While working with Mesh Mixer, we can not only remove unnecessary structures. It is also possible to add or replace structures. This is very helpful if you need to add key points to define the orientation of the parts or if you want to add simple geometric structures. In this case, we add a sphere to each hip bone to create a key. Subtracting the same sphere from the sacrum in the area of the iliosacral joint creates a corresponding keyhole which will later on help to define the correct placement of the hip bone and the sacrum. We also replaced the segmented model of the screw with a simplified version. Compared to the original model, the model now looks cleaner and more realistic. The file size has been reduced by 75%, which is really good if this model is to be used with augmented or virtual reality devices. With the digital model finally ready to print, we can move on to the next step, which is, of course, 3D printing. As the model represents rigid bone structures and there are no special mechanical or medical requirements to the material, we use common FDM technology. The final model consists of 5 parts: left and right hip bone, sacrum, a bolt and a nut. The total print time was about 16 hours for all parts plus 30 minutes of post-processing. The bone replicas were glued together using the embedded keys as alignment reference. Finally, the nut and bolt replica was inserted and locked in places. The final model gives a very good and precise overview of the patient's special pathological situation and represents the case with a high level of detail. The total time spent to create the model was about 24 hours or 2 working days. After the model was delivered to the hospital, the medical team was able to test and train the desired procedure. Besides the main advantage of training the procedure before the patient goes into surgery, the model also works as a training tool for younger physicians after the intervention. The model can be reprinted multiple times and used for simulation and training or to find a better treatment for patients suffering from the same problem. If you would like to download the model, please follow the link in the video or the description below. This link will bring you to our 3D online platform where you can also download other case-related models. This brings me to the end of today's case study. If you liked this video, please subscribe. This will also ensure that you receive a notification when we upload the next HumanX medical case study. If you have a case you would like to share with us and the audience, please feel free to contact us or write it in the comments below. Thank you, and see you next time to HumanX medical case study number 3.